That is Professor Mikael Johansson, quantum strategist at CSC. And Mikael, thank you for being here. Floor is yours.
Thanks for having me. It's a great conference so far, and I'm sure it will continue. Maybe if we skip this next half hour. Yes. No, the program is really excellent, and I'm really enjoying this.
Thank you.
Anyway, my topic today will be on pooling HPC and quantum resources across borders from a Nordic perspective, and we'll see what it means. Okay, so switching next, but maybe a quick background to CSC and what we are. So we are maybe the Chineka of Finland in a way, but Finland is a smaller country, so we are the only supercomputing center in Finland, and of course these days we do much more than supercomputing as well, or provide computing services, but that's where it all started 50 years ago, and the UNIVAC 1108 was the first supercomputer we were hosting for our customers, and these days we have grown a bit more, and still last week we had a very nice round number of employees. We were 512, which in binary is very nicely round, but this week we got one more, so now we are 513 people. But in general we are a non-profit company owned by the Finnish state and higher education institutions. The topic of today is Nordic Quest, and that's a cross-border collaboration and integration, and we have 7 partners from 5 countries, and it's a project that starts soon in March next year. The general idea here is to combine several HPC resources and quantum computers into one unified platform in a type of an HPC plus NQC service, if you will. The main hardware components in the beginning will be the CAL 9000 computers in Sweden, developed by Chalmers and the Wallenberg Center for Quantum Technology, and the Finnish quantum computer by VTT in collaboration with IQM, and the HPC resources will be Lumi, the Euro HPC pre-exascale computer, and EX3, an experimental platform for high performance computing that we have in Norway. In a bit more detail, the partners here. So as mentioned, we are 7, and it's Chalmers, CSC, the Danish Technical University, and Simula and Sintef from Norway, University of Tartu in Estonia, and VTT again from Finland. And all of this is funded by the Nordic E-Infrastructure Collaboration, NAIC, that in general wants to promote Nordic collaboration in the field of e-infrastructures. The background motivation for Nordic Quest is that individually the Nordic countries are relatively small, at least if we compare to Germany, France, UK, traditional strong quantum countries within Europe. But by pooling these national resources, we really can create something that is larger than the sum of parts. And even if it is a cliche, it is true in this case, because one needs sort of a critical mass before one can start actually achieving something useful. And another motivation for this is that the Nordic region, also including Estonia, has a solid and established competence in traditional software development for standard computers, and on average, actually 1.6% of the population in the Nordics are software developers, and that's about 60% higher than for example, Germany or the US. So sitting in front of a computer and coding is popular here up in the north. But to support the extension of this traditional software industry towards also quantum software development, access to a mature and easily approachable quantum computing infrastructure is crucial. It needs to be easy for the people. One is not supposed to be a quantum physicist in order to actually be able to start programming and developing programs. And Nordic West aims to really provide this low barrier access to quantum computing and HPC plus quantum computing, with the idea of reaching students at various levels as well as professionals. So we also actively want to go in for getting quantum computing already at high school level and maybe even earlier, at least introductions. And being a Nordic collaboration between and under an umbrella organization of rather low bureaucracy, we also hope to be easy to approach. And one thing that helps here is also that we really are spread out all over the region, so one can contact your local representative in an easy way. And I think this really is an important aspect of getting users engaged. It is always easier to get in contact with someone from your own country, even if it is an international collaboration. That's just a fact of how things go, in my experience. Okay, the tasks of Nordic West, well, these are just directly from the work plan. So, but it starts with charting the needs and interest for a Nordic quantum computing platform, both for education and for science. And then the idea is that we customize this platform to the needs and requirements of the Nordic region and really to the customers, the universities, the industry that we have here. With limited resources, one cannot do everything, so one has to choose, and then we want to choose something that is as useful as possible for as many as possible of our potential end users. And then part of it is also to, well, create these algorithm and example program libraries, so it should be easy to start exploring this field. On the more practical side, of course, also connecting and integrating these physical quantum computers to this common cloud-based platform is really central to the whole project. And we also want to integrate quantum computer simulators / emulators. So as this is really important for understanding how quantum computers work, and Luigi gave also already mentioned why actually simulators are important as well. So that's part of the project. And naturally then dissemination and communication, because we also want to really tell our users and the community what is going on and then attract more interested users here. And we go for this distributed approach to high performance computing and quantum computing, and then this decentralized approach, among other things, so it really enables diversity by just in the end easily connecting several different quantum computers under the same platform. This also means that this hybrid HPC plus QC is built in from the beginning when we really attach it to pre-exascale machines or platforms. And we'll get into this a bit more, but also low latency algorithm will be enabled by classical hardware co-located with the quantum hardware. So, but we'll get into discussion of that next. But first, an overview of different ways of connecting HPC and quantum computing. So I've divided it here into three main ways. I'm sure one can divide it in different ways as well, but I will say that these at least represent somehow the different approaches. So we have the standalone, cloud access, the co-located or on-premise way where you have the quantum computer sitting next to the HPC infrastructure servers, and then we have the distributed one where the QPU or QPUs and the HPC resources are physically distant. These come with different levels of complexity for the software stack. So the first one, the standalone, is the easiest to implement, but it also then comes with a medium to high latency between quantum and classical part, which might be a problem. The co-located and distributed parts require more integration work for the software stack, but then the advantage is that then one really, in both cases, get low latency applications to run. And the importance of latency should not be overlooked. So here's a recent report, or expert opinion on quantum computers for high performance computing by Oak Ridge and AQT. Here they have divided typical tasks that one would run and the times, execution times they take, and we see that for the low or fast algorithms, we in principle here in this figure only have error correction. And error correction, I will not consider that today. That is something that will anyway have to be at an extremely low latency and then built into the QPU already at low level. So that is separate from normal applications, so to say. But that is of course something that it doesn't help if you have your standard classical computer 1 meter away. So it's still too far. You really need to do this on chip or something. But otherwise, they consider here mostly quantum circuits that would take on the order of a second to run. And with 1 second execution times, of course, latency is not really an issue anymore. But I would say that in hybrid algorithms, and I think most agree, then latency can become an issue. And here's just I find this article very, very nicely written, and then the figure is you have of course seen a similar figure many times, all of you, before. But the idea anyway in the hybrid algorithm to having a tight loop quantum block and a classical block of a calculation. So here, when both the quantum block and the classical block are fast, the communication has to be even faster to avoid bottlenecks. So if the quantum block is very short, then latency has to be low. Otherwise, you run into artificial lengthening of the runtimes. And now with present QPUs, decoherence forces the quantum block to be fast, because we have to have very short algorithms, very, very low depth circuits, because otherwise we just get noise out of the quantum computer. So for quick loops, the standalone approach creates too much overhead, so that's dead. We really need a classical processing unit, a server, or a node of an HPC system that is physically close to the QPU, so it keeps feeding it with new input. But it's important to note that this is not an HPC task. So a powerful server here in connection with the QPU is more than enough for the foreseeable future, at least. And another point to note is also that when QPUs mature to this point where they actually provide some quantum advantage, runtimes of the quantum blocks will also increase. One popular hybrid algorithm, the QAOA, is expected or estimated to require circuit depths that approach 1 million gates. And that's well beyond what can be done on present day quantum computers, but at one day I'm sure that it will be possible to do this. But when it becomes possible, then latency is not that important anymore. but one can see that from a simple calculation on the execution times of this algorithm. So here's just some typical execution times of gate operations on both superconducting and trapped ion on systems. So 2-qubit gates are usually the most important ones anyway, and even the fastest there we are talking about 100 nanoseconds or so. But if you compute from this what the execution of 1 million gates would take, even if you would just consider the fastest 1-qubit gates of 20 nanoseconds, then this circuit would take 200 milliseconds to execute. And this still doesn't include any readout or initialization of the qubits, which would add at present time plenty to this estimate, but hopefully those times will also go down. But a signal in a light cable fiber travels at around 200,000 kilometers per second, so we get around the Earth in this time. So this means that the classical server doesn't really need to be that close here. So here, even the standalone model again becomes relevant when the quantum computers are powerful enough. Another example here, just from the IBM and Goldman Sachs collaboration, where they looked at derivative pricing. So well, first of all, we see that quantum advantage is still some time away. So they predict one is 8,000 logical qubits and the T depth of 54 million, and that execution of these programs would be on the order of a second. And of course, this also means that latency is not important. But variational quantum eigensolvers and that family. So this is one where latency really can become important. This is there's big efforts towards reducing the gate count for VQE, because VQE is promising, is one of the most promising ones or for near-term quantum advantage. And this is just a recent paper from Cambridge of one of the more successful implementations of VQE, a version of Adapt VQE. And here's an example that they had on beryllium hydride calculation, and to get a moderate error in the energy here with respect to the correct answer, one would need about a 40 qubits depth here, and that's doable without problems, and that also is very fast. But when we increase the system size here, well, the worst scale scaling is n to the third with the amount of basis functions, for example. And now we have to remember that beryllium hydride is a trivial computation for a laptop, and supercomputers can easily handle thousands of basis functions for routine electronic structure calculations. And to reach this, it again requires millions in depth of the circuit. So we again increase the time of the execution of the quantum block to something that doesn't really make latency an issue. But if you have strongly correlated but low electron number systems, then this method, I would say, is very promising. We can get highly accurate energies, and even when one has a low number of electrons, and these highly correlated systems again are difficult for supercomputers. So as long as the dimensionality of the problem doesn't grow too much, but it's still a tricky electronic structure, then I think that here VQE really can provide something usefully in the near term, and then latency becomes an issue. So low latency between the classical quantum can be important also in the future, even if one is able to execute long circuits. There might be plenty of algorithms that also can be run with shorter quantum circuits. And here then one can either use this separate server or one HPC node to take care of the classical computing that requires the low latency, so optimizing the parameters in QAOA or whatever. And well, so we have these two different models left, the co-located or distributed, and the straightforward approach is, of course, to co-locate the quantum computer with the HPC center. And in this case, the server is just an HPC node. It becomes more involved if we have the distributed approach for low latency, because then there's a bit more work, as we will see soon. But there are other advantages to this, I would say. And this is the approach also that we are in the end aiming for in Nordic West. The software stack for a distributed approach requires somewhat more work than the co-located approach. So this is because we have to take care of one additional communication step between classical and HPC. And this does not exist in the co-located approach, because, well, then this orange node here is just one of the blue ones, so we don't have this part here. This is not completely trivial. So it requires a bit of work to take care, because now the orange server here has to communicate in two directions. The low latency one to keep feeding the QPU, and then keeping the connection also to the rest of the HPC. And also user authentication needs to be done twice, but that is a rather trivial step, of course. Another thing that this requires is that we have to have personnel at more than one physical location, because we cannot expect that either the HPC systems or the quantum computers will run without supervision. Why should one make this distributed approach work then? Well, when the software stack is in place, it becomes easy to add additional quantum computing resources, because what we need then is only the location of a classical server next to the QPU, wherever that is, plus, of course, a fiber connection to the HPC center. And this increases diversity of the platform and also inclusiveness, because one can really access several QPUs from the same platform without much hassle. And also from a collaboration point of view, it's easy to time share quantum computers or just test out quantum computers. One doesn't have to buy your own quantum computer to locate it. One can share one quantum computer between many users. So, and with limited resources, one can of course not buy everything, but one can share more. Another reason is that well, the quantum computer and the HPC system can be optimally located, separated and separately. HPC needs large data centers with sufficient and optimally also affordable electric power. Quantum computers don't really need much power and will probably not need much power in the future either. But quantum computers do need shielded environments, either for temperature or other sources of noise. And one slightly worrying study came out last summer where it was found that cosmic radiation already now starts to be a problem for quantum computers and qubit coherence. So, of course, if one starts to dig down the quantum computers below ground, it's easier if one just puts a small part there and doesn't need to dig down the entire HPC system. Or even try to just build a cellar in existing premises, or HPC premises might not be trivial either. Okay, so the conclusions for this is, I would say that, and also one of the driving spirits of Nordic West in general is collaboration, and we need to collaborate and share know-how across the quantum computing and HPC disciplines and communities. And I'm happy to see that there is coming a convergence now in Europe, and these two fields are approaching each other. But there is still work to be done, but I think that everyone starts to see that this really is important. They will not be separate. In the future, they will be intimately linked, and it will stay like this. At the same time, collaboration with the end users needs to be equally important. We need to keep in mind what we are doing this for, and it is so that the end users can run their applications faster. In the end, they are not interested in what the hardware is necessarily. They can be interested out of curiosity, but the deciding factor is, do they get some new interesting science done with the new platforms? And collaboration across national borders is crucial for Europe. It's crucial for the Nordic countries, but it's also for Europe. To keep up with international developments, we really need to all collaborate. And also, all three modes of this HPC plus QC integration, depicted here again on the right, need to be set up in Europe. The standalone model is simple to set up, but it's already useful for many tasks, and especially just for getting people to try out HPC plus quantum computing and see that it is a technology that works is important. And this is rather straightforward. And the co-located approach is a straightforward method for low latency algorithms. And algorithms that require low latency between HPC and quantum computing can emerge, even if we don't see it now, but we never know what comes up in the future. It might really be that the quantum computer really needs low latency to a very powerful classical computer, and not just a server like in the distributed approach. But the distributed approach is needed for setting up this framework for a low latency multi-QPU setup. And in a way, it also future-proofs for when a working quantum internet comes, because then it would be great to connect quantum computers that are physically distant just to build up one big whole where the quantum computing power would really increase exponentially. And in general, as with just QPU implementations, also the HPC plus QC implementations need to be diverse. All eggs in one basket is seldom a wise strategy. With this, I thank you for your attention.
Thank you, Mikael. It's very interesting talk. And is there any question for Mikael? If not, I have a curiosity that is really a stupid thing that I maybe don't understand very correctly. But the difference between the distributed and the standalone technique, because with the co-located method, you have the QPU and the HPC computer in the same location, and you can connect them using wires or something like that. But in the distributed approach, how precisely do you connect the HPC computer with the quantum computer? Via internet? Did I understand correctly?
Yes. So the quantum computer would be connected to the classical server mainly, and that is the one that keeps the algorithm running for the most part. But then that classical server is then connected over fiber to the HPC, and here
okay.
Then the parts of a larger workflow that require HPC resources would then be done at the HPC center, and as well also, of course, user authentication and all of this that comes with just setting up things would be at the HPC center. But mainly for the really heavy HPC tasks would be taken care by the HPC system, but the middleman server there would take care of running the actual calculation.
Okay, so it's sort of standalone, but an evolved standalone situation, we can say. Okay, thank you. And just another curiosity, and I saw the difference in for the trapped ion and superconducting qubits in terms of time of applying qubits gates. And so it seems that the superconducting is very better in terms of time.
Yes, for a single circuit, but of course, what is important is how many gates you can execute in procession. So if you really, in the end, it doesn't matter if the quantum computing time takes 1 second or 10 seconds if you actually get much more done. So it is the ratio between gate time and decoherence that is the important one.
Thanks a lot. This is the answer that I was looking for. Thank you, Mikael.
Thanks.